Cool. Software, yeah, amazing. Great. Can people see my screen? No, not yet, I don't think. Oh, now. Now? Yeah? Cool. Is there some way? Yes, great. So I'll just have the, oh, it floats, that's great. Cool. So yeah, welcome everyone to the official talk. Let's get into it. So, all right. I don't know, probably people don't need so much motivation, but can people see everything okay? Is everything a good size? Great. Cool. So just to motivate things a little bit, what do recursive snarks let you do? At a very high level, what they let you do is construct proofs in the same way that you would with snarks, in such a way that those proofs can be combined in flexible ways. So basically what they let you do is design systems of computations that you want to perform in such a way that those computations can be, can protect various users' privacy in subtle or arbitrarily specified ways, and also can be combined by potentially other parties who may have access to other information and so on. So just a few examples of what sort of things can be accomplished. I feel like these have animation, so let's see. Okay, so these were imported from PowerPoint, so they might not look so great, but so that's life. So okay, a really simple example is, let's say you have a snark, and you have some statement, and you produce a proof pi1 of that statement. And then sometime later, another statement comes along, S2, and you would like to produce a proof of the conjunction of S1 with S2 without having to say, reprove S1. So recursive snarks, for example, would make it possible to do that. And so on, you could also, a new statement comes along, S3, and then you could produce a proof which is of the conjunction of all three statements, for example. And recursive snarks would let you do this in a way that you would only need O of 1 additional effort with each new statement. So yeah, that's kind of like a really basic example. Another kind of interesting example, potentially, is that of having some kind of auditability of machine learning models. So usually machine learning models are a bit of a black box. Here, let's say you're making a self-driving car. Oh, manage participants, I think I need to let someone in. Oh, produce, cool. Are a bit of a black box. So you would like to have some kind of visibility into that black box. For example, especially if it started doing things that you didn't want it to do, like saying that a red light was actually a green light, would be a bit troubling. And for example, what you could do is you could use snarks to prove statements of the form, oh, this machine learning model that I have, it was actually trained on this set of data, so that later someone could come and spot check the data and make sure that there were no accidental red lights that snuck in there, and if there were, here's how they got in there or something. Another example that you might consider is that of, this is kind of similar, say proving a machine learning model wasn't trained on your data. So let's say you have some adversary, for example, this guy, and you are this computer user over here. And you wanted to say to the adversary, hey, please don't use my profile when training your model. And your adversary, they tell you, yep, I did it, no problem. That's funny. This was in the original PowerPoint. This was some monospace font. It's funny that they replaced it with this weird font. Someone is unmuted. I'm gonna try and mute them. I'm not sure who it is. Okay. Oh yeah. So, right. So, the adversary tells you, oh yeah, I did it. Don't worry, I excluded it. And, you tell them, hey, can you provide me with some evidence of that? That my, in this particular model that my data was sent in. And they'll just say, well, you should really just trust me. Well, we all know how that goes. Generally speaking, it's not a great idea. It would be nice if we could have some kind of more convincing assurances that, in fact, our data was excluded from the training of some model. Yeah, another thing you could do is have some kind of, whenever you have some kind of distributed computation in which you would like the nodes in the computation to have privacy, or perhaps the nodes who are doing the computation are untrusted, you can use snarks to make it possible to perform that computation in such a way that the final result can be audited and believed, even if the nodes performing the computation are not trustworthy. The first time I did this, I like drew on arrows and stuff, but I don't have a tablet where I can draw things on. So you'll just have to imagine that like I drew like you'll just have to imagine that I drew arrows over this. And is the example kind of clear anyway? That of like a parallel computation where the intermediate nodes may be malicious. Say this is malicious, this is good, this is malicious, this is good. You can still perform the whole computation and have a convincing result, even if the nodes themselves, you don't necessarily trust them. Another example that I like, and I think it's good to kind of think of utopian examples also, is that of a social wealth fund. It's kind of like Zcash. So, the way that things work in our society nowadays is we have some, adversaries who decide how the productive resources of society are allocated. And, they do it in ways that are undemocratic. It would be nice, well, some people think, if perhaps we could have a more democratic system where maybe it's one person, one vote, or some such, in terms of how the productive resources of society are allocated. But on the other hand, you would want people to be able to maybe do complicated things like delegate their vote to some organization that they trust. Maybe I'm like, well, I don't know all the intricacies of all policies, but I trust Sierra Club when it comes to environmental policies. So I want to delegate my, some fraction of my share of my resources, at least when it comes to environmental issues, to Sierra Club. And also perhaps you'd like to do that in a way which is privacy preserving, because maybe I work for an oil company, and so I don't want my boss to know that I'm delegating to Sierra Club. They probably wouldn't like that. So that's a really cool thing that you could use snarks for to accomplish this functionality. And moreover, you could use proof composition or recursive snarks to make it possible for everyone in the society to actually verify that the process of everyone voting on how they want the capital to be allocated, you could make it possible for anyone in the society to actually verify that result. So you could sort of combine together everyone's proofs to get one sort of mega proof that shows, yeah, this is what everyone voted on. And that proof would be so easy to check that really anyone checking it would be within anyone's reach. Anyone could audit, which is really kind of what you want. Otherwise, it's not totally clear. Like, with elections, like, was an election fair? I don't know. Who knows? There's not really a way to audit it for the typical person anyway. So yeah, and then another example that I'm working on day to day is succinct blockchains, which is basically the idea of having a blockchain which, rather than requiring an amount of time to verify, which is linear in the history of the blockchain, is a blockchain which can be checked in an amount of time which is constant, so that you can have the full security guarantees on a very lightweight device like a phone. Cool. So that's some some motivations of why you might be interested in proof composition or recursive snarks in general. They allow you to make very powerful systems of verifiable computation. Before I move on to the formalism that I think is a good formalism, are there any questions or things that people want to just, I don't know, questions, I guess, yeah, at this point? No, everyone good? Let's see. Can someone give me a hands up so I know that they're good? Or can people hear me? Oh, great. Thank you, Georgios. Always with the hands. Okay, great. All is good. All right. Wonderful. Wunderbar. So, yeah, so let's get into it. Okay. So, this is like my version of a PowerPoint. It's a giant document. I'm just going to move around. Social wealth is just voting. Yeah, so it would be voting, but maybe with like, you know, complicated, maybe you have some kind of complicated rules or policy around around voting. So like maybe you want to say that people who, I don't know, this is just off the top of my head. Maybe you want to say that people who work in a particular industry or can't, you know, can't vote to allocate too much money to that industry to prevent some kind of conflict of interest voting. And so you could enforce that policy in a privacy-preserving way using snarks also. I don't know. That's just a random idea. I don't know if that's a good idea. So, but the point is that you can use any kind of policy. It doesn't have to just be simple voting. Okay. Cool. So let's talk about the formalism that I think is useful. Maybe I'll like. All right. This is kind of a very general formalism that captures more or less exactly what recursive snarks let you do. I actually prefer to call them inductive snarks, but recursive snarks has more Google hits, so I guess just we're stuck with it at this point. I'm not sure, but let's say that you have a function from some space to itself, and you know, some set x to itself, and let's say you have some point to x, x0 in x. What we want to do in this example is basically to convince someone, you know, I'm going to give you x, and I'm going to give you some integer n, and I want to convince you, if you hit x0 with f n times, you will get x. Okay, is the example clear? It's just the, you know, here's x0, or here's x, here's f, and I want to convince you that if you go with x0 and you hit n times with f, that you'll get x. I don't know if this is even a good diagram, but okay, so that's the example. And suppose we want to do it in such a way that once we have a proof of, you know, f applied n times to x0 equals x, that we can update that proof to get a proof for f applied n plus 1 times to x0 is f of x. Okay, so oops. So, you know, sorry. One, you know, to kind of help us out as a formalism, let's just define the set A of pairs x and n, which satisfy, you know, x is equal to f applied n times x0. What we want to do is construct a snark for proving membership in A. Okay, so what's yeah, we want to construct a snark for proving membership in A, which lets us update proofs. Okay, so what will be useful is the following notation. A, it turns out, is an inductively defined set. What do I mean inductively defined set? I mean there is a sequence of inductive rules such that A is the smallest set satisfying those inductive rules. Okay, I won't say too much more what it means, but let's see what inductive rules. Okay, what are the rules? So the first rule says that x0, 0 is an A, right? F of f applied 0 times to x0 equals x0, okay? So this is some notation for writing inductive rules. The way the notation works is you put assumptions at the top. In this case, we have no assumptions, and you put conclusions at the bottom. Okay, so under no assumptions, it is the case that x0, 0 is an A. Good. And one more rule to characterize A. If x, comma n is an A, then f of x, comma n plus 1 is an A, right? If you apply f to x0 n times to get x, then if you apply f n plus 1 times to x0, you'll get f of x. Okay. Does this notation make sense? So here go here go assumptions. I'm drawing this with the mouse, so it might be a little messy. And here conclusion. This is some notation from logic, I guess you could say, or really type theory. Okay. Is everyone with me? I hope so. Yes. So, and if you think about it, first of all, A satisfies these rules, and A is the smallest set which satisfies these rules. That is why we say that A is an inductively defined set, which is defined by these inductive rules, because it's the smallest set which satisfies both of these rules. Smallest means it's contained in every set satisfying these rules. Okay, so here is what the technique of recursive snarks, or the technique of inductive snarks, allows us to do. It allows us to compile this set A, or rather this description of A as an inductive set, into a snark for proving membership in A in such a way that we get two provers. The first prover corresponds to the first rule. It takes no arguments, and it produces a proof. What proof? A proof that x0, 0 is an A. The second prover corresponds to this rule. It takes one argument corresponding to the one assumption, that is a member of A, along with a proof of membership in A, and it produces a proof. What proof? A proof proving the membership of the conclusion element. Okay, so that's what recursive snarks let you do. They let you compile descriptions of sets, descriptions of inductive sets, into a snark for proving membership in that set in such a way that each inductive rule yields a prover whose type has the same shape as the inductive rule. So that's the general idea. And we'll see a little bit. Let's do one more example, and then we'll see how that actually works. It's not that complicated. So here's sort of a more flexible example to give you an idea of the power of recursive snarks, and also the ease with which this formalism lets you describe the systems that we're interested in. Okay, so let's talk about a similar set. It's going to be basically the set of, instead of just fixing a base point of x0, we're going to have have that sort of be part of the statement. So what is the set? It's going to be triples x, y, n, such that if you apply fn times to x, you get y. Okay, so in other words, yeah, you get y from x by applying fn times. Okay, cool. And what this is going to allow us to do is produce proofs of applications of f in parallel. Okay, so this set A has a similar description as an inductive set. What are the rules? Okay, so the first rule says that if x is any point in x, then you can get from x to f of x by applying f one time. All right, pretty straightforward. The second rule says that if you can get from x1 to x2 in n steps, and you can get from x2 to x3 in m steps. Then you can get from x1 to x3 in n plus m steps. Okay, and if you think about it, A is characterized by this rule. Any element of A can be characterized by these rules. Any element of A, you can prove its membership in A via an iterated application of these rules. Okay, I mean, we could do maybe let's just do an example together really quickly. So, and I'm gonna bail on this example if it ends up being like too hard, but let's try. I don't know how fast I can draw things. Let's see. So, all right. So here's our rule, right? It says, I probably should have done this ahead of time. It says x1, x3. Let's say we want to prove, for example, that you can get from x1 to x10. No, probably not 10. 4. In how many steps? 3 steps, I guess. Maybe x5 in 4 steps. Let's say you want to prove that this is in A. Pretend that this looks good, please. Okay, so let's apply this rule. So if we wanted to prove that, it would suffice to prove, for example, that there was some point x3, so that you could get from x1 to x3 in 2 steps and from x3 to x5 in 2 steps. That would be sufficient. Okay, well, let's try and prove those. This is how this notation works. Let's try and prove those. So, all right, let's start with this one. We want to prove that if you can get from x1 to x3 in 2 steps. Okay, well, for that, it would suffice to prove that, again, via another application of this rule here, that first of all, you can get from x1 to x2, in 1 step. And second of all, you can get from x2 to x3 in 1 step. Okay. And then we can finish off these proofs via an application of this sort of base case rule, assuming that, for example, x2 is equal to f of x1 and x3 is equal to f of x2. Okay, so is it clear to everyone? Gradient. How this notation kind of works? Sorry, just kind of fiddling with colors here. Yeah, does the notation make sense to people? Oops. Sorry, not sure what I did. Crap. Oh, that's not great. Okay, that's fine, I guess. Trying to get the, oh, there. Yeah, everyone likes it, great. So, and notice that, why this is kind of interesting or cool, we could have produced this proof in parallel with this proof, and these individual proofs also in parallel and so on. So cool. What we get from a recursive snark system, from this description of A, is a snark for proving membership in A equipped with 2 provers. The first prover is corresponding to this base case rule. It takes the assumption, an element of X, and produces a proof of membership of this element in A. The second takes 2 elements of A equipped with proofs and produces a proof for the conclusion element. So that's the idea of how inductive rules descriptions of inductive sets can be compiled into snarks for proving membership in those sets. And this is a flexible formalism, and in my experience, a convenient one. Yeah, we can describe what this is in general. I don't know. It's, you know, it's something you can figure it out, right? Maybe. Let's not talk about it right now, I think, unless there's burning interest. Does anyone want to interrupt me? Because I'm going to move on to a new section now. I'll just wait like 30 seconds. No, okay, good. So what's next? What's next? Next is, yeah, why don't we talk about this? So, oops, how do snarks work? Well, you start off with a circuit. A circuit. Everyone says circuit. It's not a circuit, but everyone says circuit, so I will also continue to use that sort of wrong nomenclature. But you start off with a circuit, and then you obtain a prover and a verifier for that circuit, right? So this is going to be explaining how to use a regular snark, in other words, to obtain a recursive snark system. A recursive snark system is a compiler from descriptions of inductive sets to snarks for proving membership in those sets with rules corresponding to the inductive rules, with provers corresponding to the inductive rules. A regular snark system is a machine, a compiler that eats a circuit and produces a verifier and a prover for that circuit. So we're going to explain how to build a recursive snark system from a mere regular snark. Okay, how's it going to look? Well, let's explain how to go from an inductive rule to the circuit that you actually want to use your snark system on. Let's say we have an inductive rule, for example, one of this shape. It says, you know, if x1 is an A and x2 is an A, and if I have some W of type W, and also if this predicate F holds of all those values, then you may conclude that x3 is an A. Okay, fine. Well, supposing that we had some kind of verification key corresponding to a snark for proving membership in A, supposing that we had some sort of thing, we could rewrite this. Instead of saying that x1 is an A, we could say that there exists some proof pi1 such that the verifier with this verification key corresponding to membership in A and pi1, oh, and this should also have the statement x1, that all verifies. Okay, right? So instead of saying x1 is a member of A, we say there exists a proof pi1 such that pi1 convinces us of the membership of A. Why do we say that? Well, you know, x1 is an A is not a circuit. It's not a computation that we can run and check. Saying there exists pi1 proof so that a verifier algorithm accepts on the statement x1, that is something that we can put in a circuit and check. So this is a huge step, I claim, in moving us closer to our dream of implementing recursive snarks. Cool. So okay. So again, it would be similar for x2. You know, we just kind of say the same thing. Instead of saying, excuse me, x2 is an element of A, we say that there exists a proof convincing us of the statement x2 with verification key vk sub A. What is vk sub A? I don't know, but that's fine for now. Although I actually won't explain ever what is vk sub A, but because it's kind of, we can talk about it at the end if there's time. But somehow let's suppose that we already have our own verification key. Okay. Great. So, oops. Oh, all right. I suppose I can't save it. That's fine. So, now, ooh, spoilers. Let's take one step further from this kind of like more computational inductive rule to an actual circuit, right, so it's pretty clear that now this is a description of if you think about it, of a non-deterministic arithmetic circuit. It's just saying there exists x1, x2, pi1, pi2, w, such that this algorithm, this algorithm, this algorithm, right? That's what it's saying. And as a diagram, we can represent it this way. So a bit about the notation that I'll be using, visual notation, throughout the talk. This is a circuit. This kind of black boundary here will represent the walls of a circuit. Circles represent computations within a circuit or components of a circuit. And squares represent data that the circuit is operating on. And values that are poking out of the circuit represent the public input to the circuit. Cool, so square, data, circle, circuit component, this kind of thing, boundaries of circuit with corresponding public input, and that's all we'll need for now. So this is a circuit corresponding to this inductive rule here. It contains these two components, which are verifier circuits, and it also contains like F. Okay. Please, anyone stop me if they would like. It's better if it's interactive. So if anyone's confused, I don't know. Anyway. Okay. Cool. So now is a good time to describe one practical issue, which is that, as probably some people know, every Snark construction has some specific class of circuits which are particularly efficient for that construction. So usually it's circuits which are efficiently described as arithmetic circuits over some particular field. So given that we want to stick a verifier inside of, to be certified by Snark, the verifier should be in the class of circuits that are efficient for the Snark that we're going to use it with. Oh, a little hazy what F is. Oh, Ariel, F was just any arbitrary function. The idea was like, I'm just taking an example of an inductive rule and showing how it gets compiled into a circuit. So F could be, for example, let's say we wanted to make Snarks for summing up numbers. Okay, so F could be the function that checks that x3 is equal to the sum of x1 and x2. Does that make sense, Ariel? Great. Okay, so as I was saying, because we're going to stick a verifier inside of a circuit and then use a Snark proof system on it, the verifier needs to be in the class of circuits which is efficient for that proof system. We're not always so lucky, but there is an alternative which is practical, which is that of having a cycle of Snarks. What is a cycle of Snarks? It's the following kind of arrangement. It's a sequence of Snarks such that we start off with a Snark for a class of circuits C1, whose verifier is in a class C2, then a Snark for C2, whose verifier is in a class C3, and on and on and on, up to the nth Snark, which will be a Snark for some class of circuits Cn, whose verifier is in the original Snark's good circuit class. And what that means is that you can wrap a Snark obtained via the first construction into a Snark that can be verified by the first construction, whose proof which is sort of equiprovable with the original Snark statement. So yeah, so in practice, the cycles that one would probably use are cycles of length 2. So that would just be, 2 Snarks. a snark for C1 who has verifiers in C2, and a snark for C2 whose verifiers in C1. So what's the idea here? The idea is, okay, I'm not sure, I can't really add the arrow. The idea is you produce a snark with this construction, and then you use the second, but that snark is kind of bad because you can't compose it into, again, with this construction because its verifier is not in C1. Okay, so what you have to do is produce a new snark, which basically says, I ran the verifier from the first construction and it succeeded. And what that's going to yield is a snark from the second construction, which is good because that construction's verifier is in fact in C1. So the first construction can check that one, which means basically when you compose, this one's going to be checking a proof that says, I myself saw a proof and I ran the other guy's verifier on that proof. But it's going to be good because now that computation is actually efficient for this first snark. Okay. And specifically, the kinds of cycles that we know about have the following shape. Well, actually, let me defer discussing the exact cycles until a moment from now. But is this kind of idea of like wrapping up a proof so that it can be then checked again by the original construction, is that clear enough? Probably clearer to some of you who have thought about this than others, but if anyone would like to ask a question, please, now is probably a good time because this is kind of a confusing concept and it's also an important one. Oh, someone gonna talk? No. I thought someone was unmuted. Okay, well, I'll move on then. So it's this idea we can kind of wrap up a snark, so it's good. All right, so we need basically one more concept before we move on. Oh, wait, couldn't we remove the need for the cycle with a second snark? Georgios, yeah, feel free to unmute yourself if you want to ask that question in a more complete way, because I'm not quite sure what exactly you mean.
I guess my question is, the point of the cycle is to have a way to verify the proof from the second snark via the first snark.
Yeah, exactly. Yeah.
Okay.
Okay. So this is kind of actually a lie. It's not going to work exactly this way. The verifier is actually going to require, is going to have different components of it, which actually belong to different classes of circuits. So this will be a little bit of a lie, but we'll see exactly why it's a lie and how to fix it in a minute. Okay, so there is this idea of a snark coming from a so-called algebraic holographic proof system. And what is an algebraic holographic proof system? It's a proof system of the following form. In the first round, say the verifier sends the statement, then the prover will send, in the formalism, you think that they send a polynomial, but then when you compile it using cryptography, they send a commitment to a polynomial. The verifier will send some random challenge. The prover will send another polynomial, another random challenge, another polynomial. They go back and forth. You know, the prover says polynomial. The verifier says bleh. The prover says polynomial. The verifier says bleh. They do that some number of times, hopefully not too many. Then finally, the verifier says, open these polynomials at these points, and they'll give some random points to open all the polynomials at. The prover will produce a proof of the opening of the evaluations of all those polynomials at the given point. The verifier will perform some check on this opening proof, and they'll perform some arithmetic checks, compute some arithmetic equations on the actual evaluations themselves. That's the shape of an AHP snark. Oh, and then, sorry, the way that you get a snark out of this is you use fiat Shamir to replace the random challenges with calls to a random oracle. Sorry, I guess this kind of assumes that you know what a polynomial commitment scheme is, but I didn't write any material about it, so I'm not going to explain it. Unless someone's like, hey, I really want to know what a polynomial commitment scheme is, I'm confused. Please, it's okay, so just write in the chat. No. Okay, so this is the idea. This is important that you understand the shape. The prover sends some commitments to the polynomials. The verifier picks some random points to open those polynomials at. The prover produces a proof that the polynomials really do open to some particular values. The verifier checks that proof. The verifier performs some checks on the polynomial evaluations. Okay, that's what these proof systems look like. That's what these AHP snarks look like. We're going to describe how to do recursion when your proof system looks like this, because it has some unique challenges. So I'm going to sort of rearrange what the computation looks like into this kind of diagram. So here, okay, what's the deal with this diagram? So this diagram represents the computation that the verifier ultimately performs for this snark. What's the computation? Well, remember, circles are computation. There's three components of the computation. There's checking the opening proof. There's checking the arithmetic equations on the polynomial evaluations. And there's producing the verifier's random challenges via a random oracle sponge. Okay, so here the black lines are like data dependencies with these computations, like the opening check. What does it operate on? It operates on the points, the challenge points for your evaluating, the polynomial commitments, the opening proof, and also the polynomial evaluations. What does the sponge operate on? You know, how do you actually produce the random challenges? Well, it takes in the instance, statement, the commitments, that is the prover's messages, the challenge points, and it produces the challenge points. Okay, and then what does the arithmetic checks operate on? Well, it takes in statement and the polynomial evaluations and the challenge points, and it does some computation. So here we will be in a little bit of a pickle, because this verifier, it uses two fields for performing its arithmetic. The opening check will perform arithmetic in some field FQ, and the arithmetic checks will perform arithmetic in some unrelated field FP. For the kinds of snarks that we're actually using in practice, and those are ones which are instantiated using polynomial commitment schemes based on elliptic curves. So let me just say a little bit about elliptic curves, the elliptic curve based polynomial commitment schemes that you actually use to instantiate these. We're going to have two elliptic curves, I guess. Oops. I'll just draw them. So we're going to have one elliptic curve, oops, which is defined over, oops, a field FP. Sorry. And we're going to have another elliptic curve. Let me actually stick with this one curve for now. It'll be defined over a field. Sorry, I'm I'm going to make this defined over FQ. So our first elliptic curve is going to be defined over FQ, and its scalar field is going to be FP. So what do I mean its scalar field? I mean basically this elliptic curve will have order P. Okay. So this will let us build a polynomial commitment scheme for polynomials over FP, and that will let us get a snark for verifying FP arithmetic. Okay. Now, that's fine. If we can verify FP arithmetic, then we can verify part of our own verifier, namely the arithmetic checks. But there's an important part of our verifier which we cannot certify, which is the opening check. That requires actually performing group operations on this elliptic curve, which requires FQ arithmetic. So how do we fix this problem? Well, we just get another elliptic curve, oops, who has the reverse situation. So this other elliptic curve will have scalar field. It's orange because it's defined over FP. It will have scalar field FQ, and it will be defined over FP. So that means what that's going to look like, what the verifier for that's going to look like is basically the same as this verifier, but with the opening checks, the kind of arithmetic required for the opening checks and the arithmetic checks swapped. So the opening check is now going to require, for the snark, is going to require FP arithmetic, but the arithmetic checks will require FQ arithmetic. Does that concept kind of make sense? I'm using orange. Orange things are like FP related, FP-ish, and purple things are FQ-ish. People with me so far? Georgius, good. Gordon, kind of. Yeah, Gordon, you want to ask a question? If you're confused, certainly many other people are as well. Feel free to unmute yourself and ask a question. No? Okay. Oh, maybe it'd be useful to repeat why the FP of the one curve must match the FQ of the other. Oh yeah, sorry. So our goal is to, right, we have this verifier circuit here. And our goal is to stick this inside of a snark. In other words, to make a snark which certifies the execution of this verifier circuit. But we're in a little bit of a pickle. Why? Because this verifier circuit involves arithmetic over two different fields. And generally speaking, a given snark instruction will only let us certify computations which perform arithmetic in one field at a time. So that's a little bit problematic. And you know, what can we do? Well, okay, so here we have a snark that, here we have part of the computation which uses FQ arithmetic. So we'll definitely need a snark for verifying FQ arithmetic. And here's a component that verifies FP arithmetic. So we'll also definitely need a snark for verifying FP arithmetic. Okay, well, what's gonna, you know, what's that gonna look like? It's gonna come from two elliptic curves. This elliptic curve will let us certify FP arithmetic, and this elliptic curve will let us certify FQ arithmetic. And the each one kind of covers the other one's weaknesses in terms of what kinds of computations we have to verify. We'll do a really close analysis on this, and it will be kind of, I hope, become clear in a minute actually what's going on. So let's come back to our circuit. Remember, all those minutes ago, we had a circuit. It had verifiers inside of it. It also had some unrelated function f. I'm going to simplify things and just say we have one verifier, one recursive proof composition, because otherwise the picture is going to be really complicated and crazy. So we have this one circuit, it runs a verifier inside of it, and it also runs this function f. Let's blow up what that verifier looks like. it looks like the diagram that I had down here, right? Okay, it was this diagram. So if we zoom in on this verifier, this is what is going on. So as I said, inside the snark that we're snarking, we only get to do arithmetic in one field. Let's say, for example, that we can do arithmetic in FP. So if we open up the snark verifier, that's problematic because, oh, I swapped the, I guess I already swapped the colors. Okay, that's okay. If we sort of inline that verifier, it's problematic because we need to be able to perform computation in both FQ for the opening check, sorry, FP for the opening check and FQ for the arithmetic checks. So what do? We just pull the FQ stuff out of the circuit. So you see, I just took this circle and I dragged it outside of the circuit, and then all the stuff that it depended on, I also dragged outside of the circuit to be public inputs, additional public inputs. Okay. So does that make sense? This is kind of a crucial point, this idea of pulling some parts of the computation out of the circuit and having them performed outside of the circuit. Because now we're good. Now everything inside of here is FP friendly. Who's like, yeah, this sounds good. I need someone to say this sounds good, otherwise I can't move on. The whole construction is about effective computation. Oh, what do you mean by effective computation? Feel free to unmute yourself and, like, you know, use the higher bandwidth medium of human language. No, okay. Oh, the whole construction is, oh, not sure how to make this point. So the intuition is that you move all operations. Yes, Georgios. So here we have a problem, which is that the arithmetic checks cannot be performed with FP, so we just move them outside of the circuit. And then all data that these checks require, we also sort of move out as public inputs to the circuit. Okay, so let's like go forward and see how we do proof composition. Like, how is this going to iterate? So now we have outside of the circuit some FQ-ish stuff, right? There's this arithmetic checks, and then the evaluations and the challenge points are also FQ points. So what's going to happen is we'll run our prover, right? And then this circuit will get boiled down into a proof, pi 1.5. And instead of running what was inside of the circuit, we can just run the verifier on that proof with this public input, and then perform these arithmetic checks on this subset of the public input. And that will be equivalent to verifying everything that we're supposed to. Okay, so now let's inline the definition of this V. So V will look like this, okay? It will involve some opening check and also some arithmetic checks, but notice now, the opening check is now over FQ and the arithmetic check is now over FP if we're using a cycle, right? Whereas before the opening check was FP and the opening check was orange and the arithmetic check was purple. Now the opening check is purple and the arithmetic check is orange. Why? Because we used our FP snark, which results in, you know, using group elements which are defined over FQ. So our opening check is FQ, but the arithmetic checks are still FP. So that's what happens. So now we're going to use our FQ snark. What's the FQ snark going to do? Okay, we're just going to box up this whole computation, right? And we just want X2 to be kind of the real output, real public input. But again, we have a little bit of a problem, which is that our arithmetic checks are not purple. Our arithmetic checks require the other field. So what do? We pull out the arithmetic checks and all the data that it depends on, and we leave the purple stuff inside. And well, this is at this point, I'm a little concerned. Is anyone else a little concerned with how much data we're moving outside of the circuit? Raise hand if so. No one's concerned. Well, you should be. Why should you be? Because it seems that the size of our ultimate public input is dependent upon the number of recursions that we're doing. So each proof composition, we're picking up like the whole previous statement and exposing that as one of our own public inputs so that we can perform some arithmetic checks on it. That's bad because we don't want the actual statement to keep growing linearly with each composition, right? Because then it's not really a recursive snark. So we need to fix this problem somehow. And here we're kind of really getting into the nitty-gritty of how this stuff works, but this is sort of important. At the end, as a reward, you can imagine the horribly complicated thing that we're going to get to it, which actually is not even the full picture, sadly. Okay, so yeah, how do we, this is kind of a neat trick, how we actually handle this public input issue. What was the problem? The problem was that we needed to perform some arithmetic check on the statement, the previous statement. And so that forced us, because we had to move all the arithmetic checks out, that forced us to move the previous statement out as well. If only there was some way to avoid moving the previous statement out. That's what we will figure out now. So it turns out that for basically all of the AHP snarks of interest, the arithmetic check can be factored into a portion which depends on the public input and a portion which does not. The portion which depends on the public input is of the following form. It's some sum of some fixed polynomials scaled by the elements of the public input evaluated at some challenge point. Okay, so what our goal is going to be is take this purple computation and transform it into an orange computation, because then we can leave x1 inside of this orange box and we don't have to pull it out along with this purple node. So what's the trick? The trick is to use the fact that our polynomial commitments are actually additively homomorphic. So what does that mean? It means that we can compute using orange computation a commitment to the polynomial, this polynomial basically, this sum over I xi times some polynomial pi. We just compute these commitments to pi. We can do that statically. They're fixed polynomials. And then inside of the circuit, we just scale them by some elements xi, and we can compute the commitment to this overall polynomial p. And then we can request an opening proof for this polynomial p, and get at this point b, and get that opening, verify that opening proof inside of this orange computation. So we sort of effectively evaluate p without actually having to evaluate p. So that's really great, because then that means that we can leave this thing inside of the circuit. We just pull out the polynomial evaluations and challenge points, which is okay because that's a fixed size. Again, just a reminder, those are FQ thingies. Then this is what our overall verification is going to look like. We're going to verify this proof and then also perform some arithmetic checks on this stuff. When we do proof composition, we imagine inlining the verifier circuit. It looks like this. Again, we're going to try and wrap this up in a purple proof. That's going to require that we pull out this orange bit here. So we pull out the orange bit, and now we're in the following situation where our public input consists of, the orange challenge points, the orange evaluations, purple challenge points, purple evaluations, and the actual true, legit public input that we actually care about. And this is good because this is a fixed amount of data. We have 2 purple squares, 2 orange squares, and 1 blue square. And yeah, we can imagine continuing to do that. It continues, and always we have a fixed amount. If you think about it, I don't want to maybe step through all these diagrams with people because they're kind of torturous, but you will only ever have a fixed amount of data as your actual public input. It won't grow with the number of compositions, which, oh, sorry. Though this way to move orange, yes, Ariel, that's true. It sucks to do this. It's expensive. But if you think about it, it's kind of not, it's not the worst thing in the world. It requires 1 scalar multiplication, 1 fixed base scalar multiplication per public input. Does Halo do this? I have no idea. I think so. So like I was trying to figure out actually what they do last night. And there's this part in the paper where they're like, oh yeah, they have like this polynomial k, and they're like, oh, the verifier can't really evaluate k, so like they commit to it. Oh, in our setting, it will ultimately be more efficient for the prover and verifier to compute the commitment of k so that the prover can open this commitment at y on behalf of the verifier rather than requiring the verifier to evaluate k itself. So it appears that they do this. I mean, I'm inferring from this sentence that this is also what they do. Yeah. Cool. So yeah, that's the idea. The thing is also that's kind of nice. You only have to do this for one of the 2 proof systems. You don't have to do this expensive commitment in both of them. In one of them, you can just expose the public input and then let the next person do the arithmetic checks on it. So now I just want to explain one more. Now we have a pretty good idea. The basic technique is like you just like pull some parts of the verification outside of the circuit and then let the next guy sort of finish it off. Now I just want to discuss one more thing, which is just really so cool from the Halo paper, which is this idea of sort of I wasn't really sure what to call it. They call it like nested amortization or something, but it's also the batchability is important too. This is this idea. This is the following idea. Okay, so let's say we have an NP set. That's a set of the form, set of x's such that there's some w making this relation x on x and w true. Let's call some kind of thing, a nestedly amortizable batchable argument system. I apologize for the number of adjectives. Is a collection of algorithms. It's a proof system for proving membership in A, which has the following shape. You can prove, let's start with proof. You can prove a whole list of statements all at the same time. Okay, so if you have a list of X statement witness pairs, you can produce a single proof for all of them. You can sort of verify a whole list at once, but what's going to happen when you verify is the verifier is going to spit out an instance, and a new instance. And the thing is, this new instance, it's basically the way it's going to work is that if this instance is an A, then the whole list is actually, good and is also an A. So it's like we're having a conversation. And I'm like, hey, can you convince me about like things 1, 2, and 3? And you're like, you can somehow convince me that yeah, 1, 2, and 3 are true so long as 4 is true. Then I'm like, oh, well, okay, 4. How do I know 4 is true? Well, you can actually check 4 on your own, but it will be expensive. So the way that it works is this instance which comes out of the verifier, you can actually produce the witness corresponding to this instance, given the same batch of statements and proof. You can produce the witness, but it will take a while for you to do that. So you'd rather not. But the thing is, what you can do is you can, you have this thing. You could check it on your own. It's expensive to do so. But if a prover is going to be proving to you more things anyway later on, you can just ask them to prove to you later on something also about this, that this instance is true, and included in the next batch of proofs, you could say. And specifically, what this is used for is this is how Halo is able to achieve proof composition only relying on discrete log assumption, is that they start from a proof system which is not really succinct. They start with a polynomial commitment scheme which is not really succinct, but is sort of nestedly amortizable, batchable succinct. And what that means is when the verifier, no, where is it? Sorry. What that means is when the verifier runs the opening check for this commitment scheme, it will not be able to verify it completely, but it will get a description of a polynomial along with a commitment to that polynomial. And so long as this commitment is indeed a commitment to the description, to the polynomial with this description, the verification succeeds. Does that make sense? So like, it's a polynomial commitment check which cannot verify, which you can't succinctly verify the whole opening, polynomial commitment opening succinctly, but you can use the verification algorithm to produce a succinct description of a polynomial along with a commitment, such that if this commitment really is a commitment corresponding to the succinct description, then the whole verification succeeds. That's the idea. And then what's really cool is you have a succinct description of this polynomial, and you have a supposed commitment to this polynomial. What you can do is when you do the next time you're going to do a polynomial commitment opening proof, you can ask the prover to include an opening of this commitment to some evaluation at a random point. And the point is the verifier can compute the evaluation themselves because B has a succinct description. This polynomial B has a succinct description. So what's going to happen, like we do the same dance, this is the public input. It now includes this sort of unfinished, unchecked description of B and commitment to B. Again, more recursion, blah, 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 blah. Okay, and then the next time you do a proof, you're going to basically ask the prover to batch in with the commitments that they were already working on, this new commitment to this polynomial B, and you ask them further to include in the evaluations of B. And the evaluations of B you can compute yourself as the verifier from the description. And yeah, then you'll just get one big proof that batches in the previous B with the new polynomials that the prover was working with anyway. I know this is a little confusing, but yeah, so this is an important way that you can avoid having to do the linear work of performing the verification. The final verification on the commitment. Cool. So yeah, that's really all I wanted to talk about. Are there any questions or anything that people would like me to say more in depth on? How do you bootstrap / start a recursion? Oh yeah, so there's two ways. Either you can start with a circuit which doesn't have any predecessor circuits, or you kind of like start with a dummy proof and say that it's okay if the dummy proof doesn't verify if the statement has some base case statement. And actually, so I want to let me just kind of shout out this kind of compiler that I described is from a sequence of inductive rules to a recursive proof system is implemented as the Pickles library. And let me just show you what a usage looks like, because it's, I think, pretty cool. I need to like find my branch. It's on a branch right now. It hasn't been merged. Pickles. It's called Pickles because it's a delicious food. So, yeah. So here's, can you increase the font size? Yes, I can. So here is sort of a kind of a silly example. This, let's see, what even is this? Let's read the code. Okay, so this is a proof system with two rules. The first rule has no previous proofs, and all it does is it asserts that its statement, it asserts that the public input is a square, and then it just does some junk stuff. I don't know why I put this here, but I think it's because I had some edge case where if a constraint system was too small, it wouldn't work. What is the other rule? It has two predecessor proofs, both of kind, myself. And what does it assert? It asserts that the result should be equal to the product of the left and the right, of the left predecessor and the right predecessor. So what is the ultimate top level statement going to prove? It's going to prove this is some field element which is a product of squares. Okay, interesting, I suppose. And yeah, and then so what the library does is you pass it in this description of the inductive set into the compile function, and it produces for you two provers, one for each inductive rule, base and merge. This tag thing, that's kind of like a implementation detail, and then also a module representing the type of proofs so that you can verify them and so on. And you can do complicated things like this is a proof system that an inductive snark that takes one of the predecessors of kind myself, one predecessor of kind GXN snark, which was this one that we defined up here. And yeah, so that's kind of it. I think it's a pretty cool library. Don't look at the implementation because it's not so beautiful, but the ultimate top level interface is kind of cool, I think, except for, I mean, this is sort of boilerplate that you have to write, which is too bad, but overall, I think pretty close encoding of the concept of just like writing down the inductive rules, defining the set. Any other questions?
Could you perhaps explain what is the core difference in the MNT 4.6 like recursion technique and this?
Yes, so you could also do this with the MNT 4.6 cycle. The advantage of this is basically that you don't have to use those giant S fields. So with the MNT cycles, you need to use these really big fields that have something like, well, a good one has like 753 bits. So with this technique, you get to use a curve that has higher embedding degree, which means, or perhaps maybe does not have a pairing at all, if you like, which means that you can use a much smaller field size on the order of, say, 384 bits, or maybe even if you don't want to use a pairing, 256 bits. Yep, that's the main advantage.
And maybe you could also talk about how this compares with doing operations inside, like without any field arithmetic, but doing normal arithmetic with range proofs inside. So this is what I believe Zach is in this chat, so maybe he can actually restate my question better. But the question is, the goal is to do field operations inside the snark, correct?
the goal is to implement recursive snarks. I don't know. Izaki says yes, I guess. I'm not sure to it though.
No, I think he's answering a different way.
Okay. Could you ask the question a different way?
Yeah, I'm trying to phrase it well. So the initial problem was that the verifier is doing operations on a different field
right.
than the one in the snark.
So you're asking like, oh, could you simulate the other field arithmetic?
Yes.
The non-native field arithmetic. Yeah.
Yes.
I tried doing that. It was okay. It wasn't the worst thing in the world. You can do it. I don't think you'd want to do it for the whole. You definitely wouldn't want to do it for the whole verifier. Like for example, right? So like the opening check. Okay. So like if you're not using a cycle, I already drew this as if I was using a cycle, but if you're not using a cycle, oops. The opening check is going to be like, the opposite field of the arithmetic that you have. So, oops. So these arithmetic checks are like pretty cheap, and you could probably, get away with using the wrong field for the arithmetic checks, but the opening check is quite expensive because it requires some scalar multiplications on elliptic curves, and that would be very expensive to simulate. I don't think you would want to do that. I don't think that would be very practical, but yeah. Probably for the arithmetic checks you could get away with it, but for the opening check it's very expensive. Henry, yeah, do you want to go ahead?
Okay, yeah, so I have basically my question is about the you could also do this with M&T curves and whatever. So it seems like to get inductive composition of snarks, there's like two ways that you could do that. One is you do something like Halo or something like Pickles, and you do all these cool proof techniques. And then the other is you say like, oh, I just like use a cycle of pairing friendly curves. Is that like sort of structurally?
They're kind of the same technique, but like you just have to like fix more problems when you don't have a cycle of pairing friendly curves. But yeah, you can do it with a cycle of pairing friendly curves.
So the question that I have is basically like, let's suppose that it were like magically possible. Like suppose someone tomorrow, found a better cycle.
Oh yeah, then you'd probably just want to use. You'd probably just want to use that.
Cool. I mean, that's obviously much harder to do. Yeah. So I guess what I'm trying to ask is like, is the drive to develop all these kinds of techniques driven primarily by the belief that there's not going to be kind of near-term progress on that?
Yeah, I think so. Like, yeah.
I mean, there is still an issue that you would, for most of these universal snarks, you need to do some non-native field arithmetic. So a better cycle, pairing-friendly cycle, wouldn't help with that aspect of.
That's a good point.
Cool.
Okay, so there's one question in the chat. How do you instantiate this construction? The branch name suggests Marlin HP with glog commitments on both sides. Yeah, so the way that it's instantiated currently is Marlin for both HP for both proof systems. You have total. I mean, you could mix and match if there was some reason to. And then on one side we use a pairing-based commitment scheme, and on the other one we use the DLog-based one. And the reason for that is just that the prover for the pairing-based scheme as well as the verifier are more efficient. So you sort of squeeze out a little bit of efficiency that way. Cool. Any other questions? Everyone good? Yeah, I guess so. Maybe I'll just wait one more minute, just in case anyone thinks of anything. Thanks. Yeah, thanks, Ariel, for coming. Okay, so yeah, thanks, everyone. It was a good chat. If you're, want to talk more, please get in touch, or yeah, that's all I got. Enjoy the rest of your day.